lecture number 2. That is, we will cover p-test and a ratio test in this lecture. So what is p-test series? The theorem says that the series sigma 1 upon n to the power p, n goes from 1 to infinity, which is look like as 1 by 1 to the power p plus 1 upon 2 to the power p plus 1 upon 3 to the power p plus dot 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 is convergent if p greater than 1 and diverges if p is less than equal to 1. Of course, the proof of this theorem we will not prove time being, but we will assume this result without proof. We will prove this result in upcoming lectures. So, for example, so you could see that series 1 upon n square is convergent. The explanation for this, p is equal to 2 over here, which is greater than 1, so it is convergent. Similarly, series 1 upon n to the power 5 by 2 is convergent. The explanation, p is equal to 5 by 2, which is greater than 1, hence it is convergent. Third, series 1 upon n is divergent because your p value is 1 here, which is less than equal to 1. So by p set it is divergent. And fourth one, series 1 upon root n is again divergent because p is equal to half, which is less than equal to 1. So looking at the series, we can easily identify whether it is in p series or not. I want to recall you two theorems which you have already studied in first year BSc, that is called as a monotonic theorem. So series an goes from 1 to infinity is convergent if and only if first series an is bounded above and second series an is monotonic increasing. So a convergent can be replaced with the two following cases. One is sequence should be bounded above and your sequence should be monotonic increasing. On similar line, there is sequence an is convergent. One may say that if and only if sequence an is bounded below And the second condition, sequence an should be monotonic decreasing sequence. So these two conditions can be replaced by sequence an is convergent. So now we will do a theorem which is called as comparison test. The statement of the theorem is, let an series an bn are series with non-negative terms with your an is always less than equal to bn for all n belongs to natural number, then number 1, series an converges if series bn converges, and number 2, series bn diverges if series an diverges. So let's prove the theorem 1. So it is given that number 1, series an and series bn are series with non-negative term. So both the series are positive series. Second fact is given as your an is always less than equal to bn for every n belongs to natural number. That means a1 is less than equal to b1, a2 is less than b2, so on and so forth. And the third one is series bn is convergent. We are proving the theorem number 1. That is important. We have to prove that, if you go to the previous slide, we have to prove that series an convergent if bn converges. So bn converges is given, we have to prove that series an is convergent. So we have to prove that series an is convergent, right? So we know that a series is convergent if its corresponding sequence of partial sum is convergent. Since series bn is convergent, which is our given fact number 3, so this would imply the corresponding sequence of partial sum is convergent. So let's form a sequence of partial sum. That sequence of partial sum we call it as an Tn, which is b1 plus b2 plus dot 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 bn, so which is equal to summation I goes from 1 to n bi. So this sequence Tn is convergent. Sequence Tn is convergent. Why it is convergent? Because the series Bn is convergent if and only if its corresponding sequence of partial sum is convergent, and here corresponding sequence of partial sum is Tn. So is convergent, and say converges to T. Say converges to T. Right. So that is limit as n goes to infinity of Tn, which is same as summation I goes from 1 to infinity of bi. This infinite sum is my T. let's number this as one equation. So let's call it an equation A. So our target is to show that series an is convergent. So let's form a corresponding sequence of partial sum. So let Sn is equal to a1 plus a2 plus dot 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 an be a corresponding sequence of partial sum for series an. So that would clearly imply Sn is always less than equal to Sn plus 1. Sn plus 1 you will observe that Sn plus 1 is same as Sn plus An plus 1, because Sn plus 1 will have a1 plus a2 plus a3 plus dot 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 An plus An plus 1, and this An plus 1 is positive because n uh, every An is greater than 0. So this is very clear, Sn is always less than equal to Sn plus 1. So this would imply your sequence Sn is monotonic increasing. So let's number this as an equation B. Also a1 plus a2 plus dot 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 an is always less than equal to b1 plus b2 plus dot 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 bn. Why this is true? Because in a given fact it is mentioned that an is always less than equal to bn for every n. So left hand side of this is nothing but your Sn, and right hand side is nothing but Tn, and your Tn is always less than equal to T. Why so? Because you will observe that your Tn is nothing but summation of first n terms, that is bi I goes from 1 to n, which is always less than equal to summation I goes from 1 to infinity bi, which is t. So Sn is less than equal to t. Let me call this as so this would imply Sn is less than equal to t for all n belongs to natural number. That would imply sequence Sn is bounded above by t. This is number C. So from B and C we can straight away say that from B and C we can say that series Sn is sequence Sn is convergent. And if the sequence Sn is convergent, then the corresponding series is An. Series An is convergent, which completes part 1 of proof. To prove the part 2, so proof of part 2. Let's see what is statement of part 2. Part 2 says that part 2 says that part 2 says no, part 2 is somewhere. I want to go on this number 2. Okay, so proof 2 says that it's a given that, give me the black pen, it is given that series AN is divergent. Series AN is divergent, and we have to prove that series BN is convergent. So the proof is by method of contradiction. Let it possible series Bn is convergent. So suppose assume that series Bn is convergent. If series Bn is convergent, and we also know that An is always less than equal to Bn for all n belongs to natural number. So if the series Bn is convergent, then the theorem just now which we proved, number 1, that says that series An is convergent. But it is given that series An is divergent, which contradicts the fact. Hence, our assumption is wrong, implies series Bn is divergent. So this would imply by theorem 1, series An is convergent, which is contradiction. Because contradiction to which fact? To given fact, series An is convergent. So our assumption was wrong. Hence series Bn is divergent. So this completes the lecture number 2. So in next lecture we will check we will solve the problems related to this ratio test and p test. Thank you.